Causey here. In this video we're going to examine some of the properties of the reciprocal of a complex number. Now here we have complex number w, and here's its reciprocal, w to the minus 1. Now what's the definition of w to the minus 1? Well, it's the complex number which, when multiplied by w, gives you 1. So if we start moving w around, you can see that w times w minus 1 does not change. It's always equal to 1. So one of the observations we can make, if you look at the angles, the principal arguments of these two complex numbers, w and its reciprocal, they appear to be the same. Now that makes sense because when you multiply two complex numbers together, you add their arguments. And of course, if the result's 1, the principal argument of 1 is 0. So the principal argument of w plus the principal argument of w to the negative 1, reciprocal of w, will equal 0. So these two would have to be positive and negative of each other. So the argument of w to the minus 1 would be the same as the negative of the argument of w. So let's get rid of that w times w minus 1 and just let's play around with moving w. You'll notice the arguments are always the negative of each other. So argument of w to the minus 1, the reciprocal of w, is always the negative of the argument of w. In this case, the argument of w is negative value, and the negative of a negative value is positive value. So there's that pairing of these angles. They're always equal but of opposite sign. So that's principal arguments. Now, we've not talked yet about the moduli. If we increase the modulus of w, then the modulus of w to the minus 1 decreases, and vice versa. If we decrease the modulus of w, the modulus of its reciprocal increases. I think we can do better than that. So if we look at the unit circle, now remember that complex numbers on the unit circle, all of them have a modulus of 1. And if we notice when w is outside that unit circle, its reciprocal is always inside the unit circle. As soon as we move w inside the unit circle, then its reciprocal lies outside that unit circle. And if we move w onto the unit circle, then you can see that its reciprocal also lies on the unit circle. So let's tighten up what we're saying somewhat, that if the modulus of w is greater than 1, the modulus of its reciprocal will be less than 1. And vice versa, if the modulus of w is less than 1, then the modulus of its reciprocal will be greater than 1. So finally, let's have a look at the polar forms of these complex numbers. And there you can see very clearly that the argument of the reciprocal as w is the negative of the argument of w. And if we choose, say, a argument of 2, a modulus of 2 for w, then you can see precisely that the modulus of its reciprocal is 1 over 2. Now if we move up to 3 for the modulus, then you can see that the modulus of the reciprocal is 1 over 3. So modulus of the reciprocal of w would be 1 over the modulus of w. So let's try and show these things mathematically. So let's assume that we've got a non-zero complex number w, and it's got a modulus of r and an argument of theta. So let's look at the reciprocal of w. So that's 1 over w. So that's 1 over r cos theta plus I sin theta. Now, one of the ways we can proceed with this is to think of 1. Let's look at the Argand diagram. Think of 1 as a complex number, and it has an argument of 0 and a modulus of 1. So it would be 1 times cos 0 plus I sin 0. Then we're faced with the division of two complex numbers in polar form, and we know how to do this from previous videos. The modulus is just the moduli divided, so we end up with 1 over r for the modulus, and the arguments we subtract. 0 minus theta would be negative theta. So what can we say from this? Well, we can say that the modulus of the reciprocal of w is 1 over r, and we know that r is the modulus of w. And that's one of the results that we'd observed previously. So let's have a look at arguments now, and we can see that the argument of the reciprocal of w is negative of the argument of w. Negative of that theta. However, there's a problem. Because remember that the argument, the principal argument of a complex number is in a very specific range. It goes from negative pi, not including negative pi, up to pi. Now, I think to try and figure out whether this is a valid deduction from what we've done here, we'll go back and look at the animation and see what it tells us. So here we are back in the Argand diagram. Here's the complex number w, and here's its reciprocal, w to the minus 1. And if we look at the polar forms, the arguments are equal, opposite sign, and that's true wherever I put the vector w, as you can see. The calculations always give me the same for w to the minus 1, but the opposite sign. However, there's a problem. Let's go to negative 1. As soon as we do that, on the diagram, the two arguments have become the same, as they should, because w to the minus 1 is the same as w for the real number negative 1. Multiplicative inverse of negative 1 is negative 1, and therefore their arguments should be the same. And up in the calculations, this calculation has not detected that. It's showing us approximately negative pi. If we add 2 pi to that and adjust it to take it into the principal argument range, then we get pi, and they're equal. So the calculation, because it's rounding, hasn't detected that it needs to do that, but the diagram down here certainly has. So if I move w away from the real axis, then bring it back, you'll see w to the negative 1 jumps as soon as it reaches a number on the real axis. Both principal arguments are then the same. So there is one exception to the rule that the argument of w to the minus 1 is the negative of the argument of w. One exception to that rule when the argument of w is pi. So we now realise that when we're involving ourselves with principal values of the argument, this certainly is true, with the one exception: the arg of w does not equal pi. If that was the case, then that would make the argument of w to the minus 1 negative pi, which is not in the required range. Another way of saying this is that it's okay, that result, provided that we have argument being from negative pi up to pi and not including pi. So there's strict inequalities in both cases. Now the final thing was the unit circle. And remember, we had a statement that said if the modulus of w is greater than 1, in other words, it lies outside the unit circle, then the modulus of the reciprocal of w is inside the unit circle, or was less than 1. So in this case, our argument would go that if that's true, then let's divide both sides by the modulus of w. Now it's a positive number greater than 1, so that inequality will still hold when we divide by a positive number. And therefore we get the statement that 1 is greater than, and we know 1 over the modulus of w is the same as the modulus of the reciprocal of w. That's the result we've got up here. And let's turn that the other way around. Modulus of w to the negative 1 is therefore less than 1, and that means that w to the minus 1 is inside the unit circle. So that's one of the observations we made. And of course there's the other one, that if the modulus of w is less than 1, we'd be slightly careful here. If we're dividing both sides of this by the modulus of w, we have to make sure it's not negative. Now remember, the modulus of w is positive, so we know that this inequality holds. The modulus of w is always a positive number unless w is 0, and where all this is assuming that w is not a 0 complex number. It's a non-zero complex numbers we're dealing with. So in this case we're dealing with a positive number greater than 0 but less than 1, so that inequality will still hold. So therefore we get 1 is less than, and that expression again is the modulus of w to the minus 1. Let's turn that the other way around. This implies the modulus of w to the minus 1 is greater than 1, and that means w to the minus 1 is outside the unit circle. And now obviously the third one is if the modulus of w is equal to 1, and therefore again we can divide both sides of that equation by the modulus of w, and we get 1 is equal to the modulus of w to the minus 1. So this is on the unit circle for w, and we've just shown therefore that w to the minus 1 is also on the unit circle. So that's the final observation that we made when we were working away with the animation. So it's now time for you to get involved. Here's 3 examples if you would like to stop the video just now and try them, and then we'll discuss the solutions. So let's first tackle example 1. So we're looking at the complex number -1 minus I, and we're asked to use polar form in our procedure to find the reciprocal of z. Let's examine where -1 minus I lies in the Argand diagram. 1 to the left, 1 down. And we can see from that diagram that the principal value of the argument is -3 pi upon 4, and the modulus is √2. Imagine a 1 by 1 square here, and this is the diagonal of it. So we have √2 for the modulus and cos -3 pi upon 4 plus I sine -3 pi upon 4. Therefore, we now know that the reciprocal will have a modulus that's 1 over the modulus of z, that's 1 over √2, and it'll have an argument that's the negative of the argument of z. So it's cos 3 pi upon 4 plus I sine 3 pi upon 4. So let's evaluate cos of 3 pi upon 4. Now that's in the second quadrant, and we're dealing with an angle of pi upon 4 in the second quadrant. And we know that the cosine of pi upon 4 is 1 upon √2, as is the sine of pi upon 4. So the cosine of 3 pi upon 4 in the second quadrant, the cosine will be negative. And in the second quadrant, the sine is positive. So sine 3 pi upon 4 will be positive 1 upon √2. Let's multiply out. 1 over √2 times 1 over √2, or negative 1 over √2 would be -1/2. And similarly, 1 over √2 times 1 over √2 is 1/2, so it's plus I times 1/2. So we get the complex number -1/2 plus 1/2 I. And that's our reciprocal using the polar form. Now, incidentally, you're not asked for this, but we could check this. Remember that z times z to the minus 1 is supposedly 1. So in this case, assuming that we got these, or that we got this answer right, then we surely will have the product of these two complex numbers giving us 1. Let's check that that's true. Now, the real part of this product will be from the first two terms. That's -1 times -1/2. And the last two terms multiplied, that'll have a negative I squared in it, which is +1 times this half. And then the outside 2 and inside 2 give us -1/2 I, and then plus 1/2 I. So they cancel, leaving us with 1/2 plus 1/2, which is 1. So we got the right answer. So now let's go back to our examples and have a look at example 2. So in this example, we're given a fact. The conjugate of a complex number z is equal to the reciprocal of z. Now remember, if z is x plus iy, its conjugate has real part x the same, the imaginary part y is now the negative of that. So with this fact, let's multiply both sides by z. Now my thinking here is that we know what z times z to the minus 1 is. So we're entitled to multiply both sides of this equation by the complex number z. And these two expressions will still be equal. Now on the left hand side, multiplying these two together, z times z bar, this is a result that you maybe have forgotten, so let's work it out again. The firsts give us x squared. The inside two, if we're multiplying these out, maybe I should indicate them as brackets. It makes it easier. The first two terms x squared, the outside two and the inside two terms cancel. The last two terms give us minus I squared, which is plus 1i times y squared. So we get x squared plus y squared. Now that might be familiar because the modulus of z, remember, is the real part squared plus the imaginary part squared, and that's square rooted. So this product is the square of the modulus of z. If we square both sides here, the square root disappears. So z times its conjugate gives us the modulus of z squared. And on the right hand side, result we're familiar with, z times z to the minus 1 will give us 1. And if we take the square root of both sides, the modulus of z we can see is equal to 1. Now, normally if we have something like x squared equals 1 and we take the square root, we'll get plus or minus 1. But remember, this modulus is always positive or equal to 0. In this case it couldn't be 0, so in this case the modulus is a positive number, so negative 1 is not allowed in this case. So we've done it. We've started with this fact that we were given and derived the fact that the modulus of z must be equal to 1. So we have one final example to do, example 3. So let's finally tackle the solution to that example. So this final example 3 happens to be the converse of example 2. Example 2, we proved that if the conjugate was equal to the reciprocal, then the modulus had to be 1. In this case, we're told the modulus of z is equal to 1, and we're trying to show that the conjugate is equal to the reciprocal. So let's have a look at the reciprocal. We know that the reciprocal is 1 over z. And we know we're trying to introduce the conjugate. We have to get the conjugate in the answer. So why don't we, in this case, since we've got a fraction, multiply top and bottom by the conjugate of z. That will certainly introduce the conjugate of z into the expression. So top line we have z conjugate of 1 times conjugate of z is just conjugate of z. Now here's a very familiar situation. Z times its conjugate, and we've already shown in the last example that that's the same as the modulus of z squared. However, we're told that the modulus of z is 1, so we have the conjugate of z divided by 1 squared, and that's just the conjugate of z, hence the result. So really we can say that the modulus of z being 1, that's true if and only if the reciprocal of z is the same as its conjugate. So we're going to have a look in the next video at this in slightly more detail. But anyway, that's Mr. Corsi signing out, and hope you enjoyed the video.